All right, welcome to The Explainer. Today, we're diving into a really huge leap forward in AI. And no, we're not talking about the usual suspects like chatbots or image generators. This is something just as game-changing. AI can now create perfect, artificial, and even programmable tabular data. You know, the stuff that runs our world. Think medical records, financial reports, all that. So yeah, let's get right into it.
So just imagine for a second, what if you could just push a button and poof, you get a perfectly realistic but totally artificial data set. I mean, a data set that has all the same patterns as real-world data, but with absolutely zero of the privacy risks. What could you even do with that kind of power? Well, this isn't science fiction anymore. It's what's happening on the frontier of AI right now.
Okay, to really get why this is such a huge deal, you gotta understand the core problem here. You see, generating images, which is already pretty mind-blowing, is actually simpler in one way. You're just dealing with pixels, right? It's uniform data. But tabular data, the stuff you find in spreadsheets, it's a whole different beast. It's just a tangled mess. You've got numbers, categories like male or female, plain old text, all jumbled together with these really complex hidden connections. Trust me, it's a way harder problem to crack.
And that brings us right to what we're calling the tabular data dilemma. Why is it so important to be able to generate these synthetic tables, and at the same time, why is it so incredibly hard?
Well, the motivation here is massive. Just think about it. We could create completely anonymous medical records for researchers, finally protecting patient privacy. Or we could whip up more examples of really rare stuff, like a specific disease or a certain type of financial fraud, so we can train our machine learning models to be way, way better. We could even use it to intelligently fill in the blanks in our datasets, or create safe, realistic data to test out new systems without ever touching real sensitive user info.
So, how in the world are researchers cracking such a tough nut? Well, the breakthrough technology actually comes from the world of image generation. It's something called a diffusion model.
Okay, so the process basically has two halves. The first part is what's called the forward process. Just imagine you have a crystal clear photo. That's our real data. The AI starts to gradually add a little bit of random noise, kind of like old school TV static, over and over again in lots of tiny steps. After a while, the original picture is totally gone, just buried in a sea of pure random noise. But here's the key part. The AI is watching and learning exactly how that image broke down, step by step.
And this is where the real magic happens. It's called the reverse process. The AI learns to do the exact opposite of what it just did. It starts with a totally fresh patch of random noise, and then, step by step, it carefully removes that noise, basically retracing its steps backward. And by mastering this whole denoising thing, the model doesn't just copy the original. No. It learns the deep down patterns so well that it can create brand new, totally realistic data from nothing more than static. It's pretty wild. But of course there's a catch. This whole process was designed for pixels, right? Which have nice continuous values. Trying to adapt that to the messy, non-continuous world of spreadsheets, that was the massive technical hurdle researchers had to figure out.
I mean, think about it. How do you add just a little bit of noise to a category like New York? You can't make it like 1% California, right? It's either one or the other. That right there is the central puzzle that needed some really brilliant solutions.
So to get around this, a couple of really clever approaches emerged. The first is something called analog bit encoding. Basically, it takes a category, converts it into binary code, zeros and ones, and then it treats each of those bits like a number it can add noise to. Pretty smart. The second approach uses a different trick. It uses a powerful AI called a variational autoencoder, or VAE, to squish the entire messy table down into a new, smooth, continuous space. And in that space, the normal diffusion process works like a charm.
Okay, so we can make realistic tables now. That's awesome. But the next big leap is about control. How do we go from making just any old realistic data to making the exact data we want whenever we want it?
Well, when it comes to control, researchers have basically come up with two different philosophies. The first one is what you could call guidance on the fly. This is what models like ReLDPM do. It uses a flexible, separate controller to sort of steer a pre-trained model while it's generating data, telling it what to do without having to retrain the whole thing. The other strategy is about baking in the rules. which is the approach a model called CUTS takes. Here, you actually fine-tune the model itself to follow a specific program of rules that you, the user, define.
And this is a perfect example of what programmable data actually means. With this framework, CUTS, you can literally write out simple commands like this one, forcing a rule where every single person generated has to be between 35 and 55 years old. You can even do more complex stuff, like making sure that if someone is listed as divorced, they can't also be listed as a husband or wife. This is unbelievably powerful.
That guidance approach from the other model, rel DDPM, is just as cool though. Think of it this way. The main diffusion model is like a self-driving car that already knows how to drive perfectly. The controller is just the GPS, giving it real-time directions. It's saying, hey, for this next batch, make 70% of the people female, or generate a record that looks like this. You're basically steering the car without ever having to pop the hood and mess with the engine.
Okay, so the theory is super impressive, right? But what's the actual payoff? Does it work in the real world? Let's take a look at some of the groundbreaking results.
All right, here's a fantastic example from rel DDPM. A ton of real-world datasets are what we call imbalanced. A classic case is fraud detection, where maybe 99.9% of transactions are totally normal. It's hard to train a model on that. So what they did was use rel DDPM to create more examples of the rare thing, the fraud. And when they did that, the performance of their fraud detection model shot way up. You can see the F1 score, which is a key measure of accuracy, gets a really nice boost. It just shows the model gets way smarter.
And now look at this. This is from CUTS. Here, the big goal was totally different. They wanted to generate data that was less biased. The demographic parity score you see there is a measure of fairness, and for that, lower is better. And what you can see is that, compared to the original data and other methods, CUTS generated synthetic data that not only kept the accuracy high, but it also made things way more fair. It's basically a new state-of-the-art for generating fair data.
So the bottom line is, these new models give us this incredible new toolkit for creating better, safer data. We can now generate what's called K-anonymous data, where any single person's information is totally hidden in a crowd. We can deliberately obscure sensitive details like the exact breakdown of patient conditions in a medical study. And like we saw, we can enforce those common sense rules like no 10-year-olds with PhDs to make sure the data isn't just statistically right, but actually makes logical sense.
Now, remember that second approach we talked about earlier, the one that works in that compressed, latent space? Well, this is where a model called TabSyn really shines. When you put it head-to-head with other top models, it just consistently comes out on top. It does a much better job of capturing those tricky, complex relationships between different columns of data, which really proves how powerful its unique strategy is.
But honestly, here's the real wow moment for TabSyn. A lot of these diffusion models, they need hundreds, sometimes thousands of steps to create just one piece of data. TabSyn can produce top-tier data in fewer than 20 steps. That is a gigantic leap in efficiency. It's what makes this tech go from a cool idea to something you can actually use in the real world. And all that speed comes from its clever design, working in that compressed space we talked about.
So, to wrap this all up, this new frontier of data generation, it isn't just about making copies of stuff. It's about engineering data with a specific purpose in mind. We can now generate data that is designed from the ground up to be more fair and less biased. Data that protects privacy. Data that fixes annoying problems like imbalanced classes. And data that follows whatever logical rules we set for it. It's really a fundamental shift, moving us from just analyzing data to actually synthesizing it.
And all of this leaves us with a really profound question for the future. Look, for so long, we've been stuck with the data we have, with all its biases and flaws. But now that we're mastering the ability to create brand new data from scratch, we have a really important choice to make. Do we just use this to make more of the same, to replicate the world exactly as it is? Or do we use this incredible power to build datasets that reflect the world we want to live in? The tool is finally in our hands. What we do with it, well, that's the next chapter.